So anyway, so we'll start about this one. So the slides are visible, right?
Yes, sir.
Okay, anyway, so last class, we have started this normal modes. Okay, so if you want to know what is inside the planet, what type of materials, metal properties, and other things, so the only way is through the seismic data. Okay, so like this large magnitude or even 6 magnitude, say. Okay, the instruments are of high good quality. We can measure, the responses, and like a non-destructive testing, we can go back and then find out, the metal properties. Okay, so that is the key. And then we have said that if there is any magnitude 6.8 and the instruments are very strong, sir, you can record several multiple orbit waves. The same thing, the whole Earth gets, these waves will travel, 4-5 times or something like that. So this data is there. So now the idea is using this data. So we will try to find out what is inside the Earth itself. Okay. And then if you try to find, if you look at the data and if you plot the Fourier amplitude spectrum, so you will see several peaks. So what the people tried to do this was, what are these peaks? They tried to find out the physics say. So they were attributed to the all the mode shapes and others also. And using that information, so we can get natural frequencies of our planet. Okay, and using the natural frequencies, so because in dynamics also they have studied root of k by m, the stiffness, and then of course the Young's modulus, p wave velocity, shear wave velocity, all those things can be estimated. So that is the idea behind this normal modes. Okay. So this already I discussed. So many earthquakes, we have recordings for 35 hours, 48 hours, 60-hour data set. And if you plot, you can identify nicely these peaks, and then it matches nicely with the data also, with the theory also. Sorry. So the concept, as already I told us yesterday, like you decompose the data in several mode shapes, okay, and then you try to identify its natural frequency and other details also. Same as structural dynamics. Okay. So last class, the first thing what we see was a fluid sphere. Okay, so it is a very easy, simple thing, because there is no shear set. Very easy to calculate. Okay, so this analytical solution we have seen, and then since it is a sphere, so you have r, delta, and then phi. Okay, the three coordinate system, the axes are different, and then we have seen like separation of variables. So you can split up into several things. So with the time, it is e to the power of I omega t, like simple harmonic. With phi also, it is e to the power of I m phi, a simple harmonic motion. But when it comes to delta and then r set, we get with respect to delta, the legendary polynomials will come into picture. And with respect to r set, you will get, these Bessel functions or the Hankel functions. And here also the interesting things was, when m is equal to 0, the azimuthal order, you will get some solution. And if m is not equal to 0, so you will get a slightly a different thing. So this YL m phi. So last class I already explained you. So this is our spherical harmonics. Okay. So they are like our sine waves and cos waves only, and they are orthogonal to each other, and all the properties, it's perfectly valid. Okay. So this also we said in the last class. And with respect to R, I showed you the spherical Hankel functions or the Bessel functions, will come into details. Okay. So for L is equal to 0 set, so this R becomes only sinusoid. We can have a closed form solution for the natural frequency. But when L is not 0 set, higher angular order, so you have to find out the zeros. It is complicated, because sine, cos, you may have to do it numerically, and then you have to plot these numbers also. So this also we discussed now, and of course orthogonality you can say. And another most important thing is degeneracy. Okay, that means 2 or 3 modes may have the same natural frequency, because it is a sphere, and we have that 0 to 2 pi, 2 pi to 4 pi. Same thing may get repeated this way or the other way. So this degeneracy also happens also. Okay. So and then of course that was, so we saw for a fluid, then the solid spheres. So this also people derive. Of course, we are not going into the detailed derivations. I'm just pointing out the important things itself. So for solid spheres, this Lamb's paper is there, and L, M, and N are this one. And so vectors is because now you are having the shear stress also, so everything becomes vectorial kind of a thing. So spherical vector harmonics comes into picture, R, S, and then T, and other things also. Okay. And another most important thing also we said was in 3D cell, you can split the problem into two 2D problems. Okay. Vertical, longitudinal, then transverse component, SV, PSV. So in sphere, we call this a spheroidal and toroidal kind of modes also. Okay. So this is how we write the displacement field. So you have a contribution from all these spherical harmonics, and then you will get in a matrix kind of a format. And if you find out eigenvalues and eigenvectors, so you will get your normal mode natural frequencies, and then its mode shapes also you can derive from these matrices. So this above is a spheroidal, the below one is a toroidal modes itself. Okay. So and of course you can incorporate force also like strains and then stresses and stress discontinuity using your Grahamel's integrals. So you can use these expressions, and finally you can use this normal mode theories. Like theoretically you can compute a seismogram using this normal mode theory also. So now the like last class also I told you the normal mode, whatever the analytical derivations, so they nicely match with the data also. So what one does is you collect the data set, you take its Fourier transform, you can easily identify these peaks and then its natural frequencies and other what modes got excited, due to that earthquake also you can find out from this data itself. Okay. So this also I told you, like sometimes many people, they take all the data and then they add it, so that the mode thing gets amplified, and you take a Fourier transforms and then you identify these mode shapes also. Okay. Now this is fine, but the Earth, when you are talking about the entire planet, so gravity plays a very important thing. And gravity, since it is a vertical cell, so it will have effect only on the spheroidal modes or on the Rayleigh waves. Toroidal modes it will not have any effect at all also. So this also the derivation is already available, like the famous Poisson's equation set. That is the one hydrostatic equilibrium, where pressure is balanced by the gravity. Like in planet, as you go inside, overburden pressure increases. So that is balanced by the gravity or whatever. So you can solve this famous Poisson's equation set. So your spheroidal mode, so this is the equation of equilibrium, you see, for a equation of motion, sorry, for a spheroidal mode. So you have additional terms actually which account for the gravity apart from other continuum mechanics things itself. So you solve in the same format, spherical harmonics and other things also. Now your equations previously it was 4 by 4 for spheroidal, but now you will be having 6 by 6, because gravity also has that k and j, extra things will be there. So now I find out eigenvalue, eigenvectors, you can get all the mode shapes also. So these are, if you plot with respect to angular order numbers and the frequency, the graph looks like this for spheroidal mode. Like last class, I already told you. So when n is equal to 0, so your Rayleigh waves, it corresponds to the Rayleigh wave modes, the higher ones. And then, if you go to this portion, so PK, IKP, PKP, so these modes, these waves, they pass through the inner core, other things also. So if you can, so now like Mars, so you can find out, given a velocity model, you can find out these type of curves, and from the data, so you can identify those frequencies and others using that information. So we can do the inversion and get back, the metal properties inside our planet itself. Okay. So the Stoney modes, where is inner core boundary, core mantle boundary. So where are the discontinuities in our planet? So all those things can be established nicely from this normal mode theory also. Okay. So this is for the toroidal modes. So toroidal modes also, you can easily find out n is equal to 0, that is a loud wave things comes. Then we will be having, SCS, then S wave, all those details you can get from the toroidal modes. Now I will just ask you in the toroidal modes, sir, can you find out outer core? Suppose if the plan in our Earth, say, if there is outer core, say, now what happens to the toroidal modes in the outer core region? Abhilash, you are there. So toroidal modes, so what happens
Yes,
in
sir.
the outer core? So for our planet Earth, what is in the outer core? Inner core, then outer core, mantle and crust. So what is there in the outer core? What type of material is outer core, Solid or a liquid?
Solid, sir.
So outer core, be careful. Inner core is solid. Outer core is?
Liquid.
So now what happens if it is a liquid, say, shear waves will not propagate, okay? So toroidal modes, so we'll have some issues. So you have to be careful, okay? So looking at the toroidal modes, looking at spheroidal modes, so we can easily find out, what is inside our planet, okay? The terrestrial planets, even Earth or other planets also, okay? So this is how we try to use this one. And these are the theoretical spectrums, you can, as already I told you, you can even use a normal mode theory. You can even simulate, the seismograms data also. like given a velocity model, the whole up to the core level, you can simulate and then you can compare with the data. And you can easily identify the phases also, what time Rayleigh waves are coming, what times love waves are coming, and you can match with the theory and you can work it out. So these are theory and these are the observed vertical components, for the same Colombian earthquake. So you can see both of them, they match very well. That's that simple, the normal mode theories, although, there are a lot of complications and nonlinear other things are there. A simple elastic theory set is able to explain, the data also. So that is the main advantage of this normal mode theory. So this is how the normal modes looks like. Okay, you would have seen in the Professor Jessica's lecture also. So this is the first mode, 0s0. Okay, so its a periodicity is 20.5 minutes actually. That means, the whole earth is a breathable mode. That's a whole volume expansion or volume, compression kind of thing. Then we have 0s2 mode. It is what they call as the football mode also. Its periodicity is 53.9, the minutes itself. So the fundamental radial mode is a 20.5 and it has no nodes at all. So everything is whole expansion, whole compression itself. But here you have the nodes itself. So this is the difference between these two. Okay. So just 1 second. Hello. 3 o'clock. IIT campus. First, so this is what we said. This is so you have these mode shapes. Okay, so the breathable mode, that's what this is. So its periodicity is a 20.5. Then this football mode, so it is 53.9 minutes itself. Okay, and similarly, say we can extract for all the. This is how it looks like. So 0s0, say. So you can see it is like whole volume, expansion or volume compression. It is also known as the breathable mode itself. Now, if you see this 0s2, that's a football mode, you can see here. These are the node points where the displacements, becomes a 0 or whatever here. So and of course the periodicity increases itself. Okay, and this is how the toroidal mode also 0 to T2 has been plotted here, and you can find out, it's a periodicity also. Okay, and of course I think there are a lot of animations. MATLAB programs are available in Google, so which will show all these animations also, how the modes, looks like, or the how Earth vibrates at this type of modes itself. Okay, and of course this is how the radial variation, the displacement Eigen Functions. So these are like, on the surface we are showing, that is M and this one, but you can also find out the displacements also, like 0 U2 say. So this mode U is this horizontal, V is the vertical displacement. So they look like this, and of course these are the traction vectors or the shear surface, the stresses basically. Okay, so this is I think 0 U2 0 VT has plotted here, like, and this is for the the 0 R to 0 S, that's the tractions. Okay, for the football mode, it has been plotted also. Okay, now this is for I think for the football mode 0 S2 has been plotted. So you can see the translation inner core boundary, of course, which has a theoretical period 325 minutes, 1s1, approximately 5.5 hours. So like this, you can find out all the mode shapes also. Like, we can easily calculate from our normal mode the theory itself. Now, not only this one, see, like one important thing also. See, like for example, say the breathable mode is, or this 0s2 mode is 53.9 minutes, say. So now, if you want to observe this mode, say, what should be the duration of your seismogram? You should be able to record for how much time?
More than 53.
More than 53 point, and more like it is double. Okay, so that means you have to record for 6 hours. So of course, if it is a small magnitude earthquakes on earth, like 1 magnitude or 2 magnitude, you will not be able to record because it dies down. Okay, but if it is a 6 magnitude or 6.8 or 9 magnitudes, then the whole earth vibrates. So you can record for 6 hours, 60 hours, 3 days, 4 days, 5 days, you can easily get this, calculate all the mode shapes also. So this is the key. Okay, so that also tells you. So if you want, of course, this is how the Eigen functions looks like with respect to depth actually. So 670 is, I think, the boundary between core mantle boundary or IC inner core boundaries are there, and you can easily find out actual. Okay, so like for example, say now, like if I see now, if we see 11s2, 15s2, say what is the speciality on the below one, these displacements. So 670 is this one core mantle boundary, and this is the inner core boundary itself. Okay. So now if I want to find out metal properties in the inner core boundary, say, so which mode will tell me? Yeah, in the ICB region. So like here also we have 2s90, 2s100, 2s110, 2s120, 2s130. So these are the displacements. Okay. But if you want to find out in ICB regions, so which mode has a high displacement there? See, this is a surface. Okay. Now in the inner core boundary set. So now which will have the highest this one? So you can see. So 6s2, 11s2, 28s2. So they will be having the high this itself. So these
6s2.
so if you find out these modes, say, so these modes will be able to tell you what type of material is there in your inner core boundary and other things also. So these are basically the key. Okay. So these modes, if you are able to observe, then easily you can calculate the natural frequency. Anyway, once you know the natural frequency, then easily you can find out stiffness, Young's modulus, shear wave velocity, P wave velocity. All other details can be observed itself. And of course, this is how the displacements, attractions. I think it is for n u naught, variety. You can plot all these things itself. Okay. So this is how the toroidal mode also looks like. That is 0 to 2 mode, and these are the displacements. See here, what is happening in the displacements after core mantle boundaries. What is happening to the displacement? Can you observe here? Displacements. All the modes, they are oscillating. And suddenly, what is happening here?
No displacement.
Now, why no displacement? Now, see, in the core mantle boundary means it is inner core mantle boundary. What is in the inner core?
Solid region.
So be careful. The inner core, what is there? Sorry, inner core it is solid, and outer core? No.
It is liquid.
Liquid. So in liquid means your shear waves will be almost velocity will be 0. Okay. So this is how it looks like. Okay. So no need to plot up to CMD because anyway it will be 0. So these are how the mode shapes looks like actually. Okay. With respect to radius of our planet. So you can plot all these displacements, attractions, and other the mode shapes. And these are some of the frequencies actually. Okay. So 0 S0 say in millihertz, it is a 0.8 millihertz. Of course, if you take reciprocal, it will be that 23 minutes or whatever I showed you. And 2 S0 say 2.51 millihertz. Okay. So now as 27 S2, so you can see the natural frequency, it increases. But here the most important thing, which mode has the lowest frequency? Can you identify in this one? So generally in our the structural dynamics say which mode will have the lowest frequency. So you will have multi-degree of freedom system. So which mode will have the lowest frequency?
1 or 2.
1 or 2? No, whatever you have solved all the problems, which one has lowest frequency? The first one only. Okay. But now here, what is happening? So which mode has the lowest frequency? Compare here, spheroidal modes.
1s.
1.
1s1.
1s1, where it is 1s1, 0.0513. Okay, so this is what they call as Lister mode itself, of course. Okay, but anyway, this to observe this one, your duration also should be very high. That's the time history. But 0s2, if you see, say 1s1 is one thing, then 0s2 also has 0.3093 millihertz itself. Okay, so this is how the modes this looks like. Okay, now just we will. So now. So you are able to see this
Yes, sir.
normal mode strengths. Okay, so these that Professor that Jessica Irwin's lecture. Okay, which I think that YouTube video I have already shared with I have posted here also. I think I hope you have listened to this video, right? So
Yes, sir.
have you gone through that YouTube video? So she
It's
has
awesome.
shown
Yeah.
nicely, and all the derivation has been taken from Aki Richards' book. Okay, so same thing. She has also shown all the things also. Now she has explained nicely, the same thing, the mode shapes and other things also. And of course, this is also one very important thing that 0s25 say this mode shape automatically, the Rayleigh waves say it also coincides with that Rayleigh wave modes also. Okay. So this also she has shown you. And the most important thing is you can see here. So this is a famous paper by Jinsky and Gilbert, okay, which has been published in the Nature, that is in the year of 1971. Say. So this paper say, so what they have done is, I think Alaska earthquake or some earthquake, they have recorded the data, and then they have done the normal mode thing, and they have found out all the the mode shapes, the natural frequencies, and all other things they have found out. And finally, say they have conveyed that they have used solid inner core, they have used a liquid inner core also. They have found out the natural frequencies, and then they have computed the errors actually. So finally, if you see here, what is our Earth consists of? Yeah. So Earth is our Earth inner core is solid or liquid. You can see here they have computed the error, relative error. So error is low. How much is here? Which is low for inner liquid inner core? It is here. Solid inner core is here actually. So which is the lowest one?
Solid inner core.
So what does it means you? So our inner core of our planet Earth is solid or liquid basically?
Solid, sir.
So this is how we try to do in normal modes. Okay. So once you put up a seismograph cell, you record the data and you observe these mode shapes, and then you take some velocity models. So you find out this one and you find out the error cell, and then you can easily find out what is inside the planet. Okay. So this is the key. Basically, why this normal mode theory is very successful, or it is widely used. Say. So in the moon or any terrestrial planet or anywhere, say. So people, if they want to know about what is inside the planet, so the only way is through this, sending a seismograph, and we should be able to record, say, okay, these are long period waves which can be excited by, some high magnitude quakes or maybe some huge impacts or whatever, so that the whole planet vibrates. Say, if you can record the whole vibration, easily you can find out into normal modes, natural frequency, metal properties, and all other things can be done through this, the normal mode theory. So that's why this theory is very, very important in planetary the seismology. Okay. So this is what she presented in her lecture also. So people tried with variety models. They do solid iron, liquid iron. They change the metal properties. They find out errors, and then they come up with a nice the model for the planets actually. Okay. So this anyway. So this is the most important thing. And then, of course, people have now the analytical solution, whatever is available. Fluid sphere is fine, solid sphere is fine, but now people have started in the layered models. Of course, you can do analytical, but you may have to do some numerical calculations and others. People have done also all these things itself. So, of course, normal mode splitting and so many things has been found out. Okay. So now, anyway, so now as far as this course is concerned, I want all of you, to go through this mathematical derivation. Okay, not in detail. You will not be able to understand. You will not be able to solve. So in today in WhatsApps, I have sent you, one manual. Okay, so I hope all of you have read it. See, I have shared you that manual. No?
Yes, sir. Many of
Minios. Okay, so I will just 1 second. I will just share this manual. So this is going to be your next assignment. Okay. So if you open that manual, you are able to see mini also.
Yes, sir.
So now what all of you have to do is, no need to worry about the mathematics. Okay. So Abhilash, no need to worry about mathematics or anything. So the software I will be sending you. Of course, you can download it in GitHub also, Minios. So this is a white software. It is a Fortran program. Okay. So what you have to do is, Abhilash, you also have to take account in Aqua Cluster. Okay. So you have to run the Fortran codes or whatever. So this codes you have to implement, and already Meenakshi and others will help you to implement this one. So this is essentially it helps you to, if you give a model parameters, like if you give a layered velocity model for our Earth, okay, like our solid sphere, fluid sphere, or whatever, it will compute, the Eigen functions. That is, the eigenvalues, eigenvectors, it will find out for your spherical model, okay? And of course, it also computes the synthetic seismograms also. You can even simulate if there is a 8 magnitude, say, how much will be the displacement, how much will be the velocity by summing up this Eigen functions itself, okay? So this is how the flow chart he has given also. So you can see installation, how to do the installation also they have given. And then, he has explained nicely how the input data has to be given. And then, you can find out all the output data, how it comes, the greens functions, everything it does, okay? So you try to implement this. I think where is that? So he has given some examples also. Okay, so you can go through the examples, and then I want you to run this code and get for Moon, Mars, as well as for Earth, say the velocities, the natural frequencies, eigenvalues, and then this is eigen functions itself. So he has done the example problems. Say like some no ocean, the frame model, that's the preliminary reference Earth model. So they have used this one. So you can see it computes spheroidal modes, toroidal modes, radial modes. They have all kinds of things there. Okay. So if you give this one, say, automatically it will give you, all the details. Okay. So you can see these are the frame model. That's the Earth model, the velocity model for that, which has been estimated from normal mode technique also. So this you can use it, and then they have done benchmarking. So all those things are done. Okay. So I suggest all of you to go through this. I will be sending you, that program also, or it is available in GitHub. Okay, if you type MiniOSSI, you can download that software. Try to implement in, already it has been implemented. You just run this one and get me the normal modes, the some things for planet Earth, for planet that's our Moon, as well as for our Earth and Mars itself. Okay, so this is going to be your next assignment. Okay. So with this, I will close, so today you follow this one. So this is your next assignment. So if there are any questions, you can ask me.
So the data for this Moon, Mars, and Earth.
That see, the velocity model is available for Mars. Some preliminary models are there. Okay, so you have to use those details. So search in Google for Moon. It is available. Garcia and others have published. So you type it in Google. Okay, that those are many papers are there.
Okay.
So get the data, and then what you have to do is